I already made reference to this quotation in the previous video. All models are wrong, some are useful. So as much as we love reservoir simulation, we know that it's not going to be an exact representation of what you have in the subsurface because we just don't know several parameters. Some of the parameters, we don't have a direct way of measuring them in the subsurface, and the only window we have into the reservoir is through the wells, and there are only a few of them in each reservoir. So it's not going to be an exact representation, but the hope is that we are able to use the numerical simulation model to evaluate how production, for instance, will change if we change the operating conditions, right? If we change different parameters in the model, we're able to evaluate what effect it's going to have on production, and that's how it becomes useful to us. We can figure out the best way to produce a well by changing the well rates and figuring out the one that gives us the highest cumulative oil production. So it's useful even though it's not an exact representation of the subsurface. How useful a model is depends on the objective for which the model was created. If the question being asked when creating the model, for instance, is the effect of spatial variation of permeability on the average pressure in the reservoir, and you're trying to use an analytical model from well testing for that purpose, then it's not going to be valuable for that purpose. Why? Because your pressure transient equations, the equations used for pressure transient analysis, assume one permeability for the entire system, right? So it wasn't developed for that purpose. So its value for evaluating the effect of spatial variation of permeability on average pressure is basically useless. But if you're to use that to predict average pressure for a reservoir, of course, the value is high, right? It becomes valuable because that's what we created that model for. We're able to extrapolate from semi-log plots of pressure and predict the average reservoir pressure. Same deal here. The value of the model depends on the modeling method you're going to use to try to answer the question. So if you're going to use a numerical model to evaluate the best operational condition for the well, meaning the constant rate or constant pressure, and what should that constant rate be, for instance. The simulation model was developed specifically for that purpose, numerical simulators, and then its value for that purpose will be high, right? It's just a case of using the right model to answer the right questions. The value of the model also depends on the way the model is constructed. Your standard Blackwell reservoir simulator assumes Darcy equation applies, meaning it's going to be applicable for laminar flow regimes. That's the assumption. That's one of the assumptions in the Darcy equation, laminar flow. So if you take your Blackwell simulator, CMG IMEX, and you apply it to gas reservoirs with very high permeabilities, where the flow rates are so high that you can actually have non-Darcy flow in the reservoir. You can have turbulent flow in the reservoir. Then what you will realize is that that model is not going to be valuable for that purpose. Your predictions of production will be wrong because Darcy equation does not apply. And you will see that there are also modifications for non-Darcy flow available in CMG. The value of a simulation model also depends on the way we use the simulation model. If you're going to use a reservoir simulation model to predict the amount of oil stored in a storage tank, so after the oil and gas get to the surface, it flows through surface facilities and ends up in a storage tank. And then you schedule liftings for people to come with their tankers and take some of the oil at specific times. So you want to know the amount of oil that will be available in the storage tank at any time. And you want to predict that using a reservoir simulator. You will realize that that's not the real purpose of the reservoir simulator. It can provide inputs that will lead to this, but just grabbing the rates from the simulator and adding it up through time and using that to predict the amount of oil in the storage tank will not be right. That's a wrong use of the simulator. So the value of the simulator for that purpose will be low. Why do you think it's going to be a bad idea to use the rates directly from the simulator to estimate what's going to be in the storage tank? The simulator will predict what the oil rates will be under ideal conditions. But we know in real life we don't have ideal conditions. There could be downtimes, right? Because the operations guys want to go change a choke or they want to fix a problem on another well. And from time to time, they keep shutting some of the wells down or sometimes shutting the entire field down. There's downtimes. So it's called downtimes. There is also operational inefficiencies. The fluid, the amount of oil you get at the wellhead will not be identical to the amount of oil that makes it to the storage tank. There will be losses, right, due to operational inefficiencies in the path of the oil from the wellhead to the storage tank. So that's an example of where the right model could be used wrongly. Numerical modeling requires complete quantification of your system. So what that means is, well, to solve your simulation, so I'm here, to solve this numerical model right here, well, you will need the porosity for every simulation cell. So for every grid block in the domain, you need porosity. You also need permeability. You need residual oil saturation, residual gas saturation if it's multiple phases. Every single grid block has to be populated with these values. And the reality is we really don't know what those parameters should be everywhere in the domain, right? At best, we have cores from a few points in the domain. So reservoir simulation actually requires lots of data. And if you provide garbage as inputs, the output you will get from the simulator will be garbage. So it's strongly dependent on the input parameters you provide, many of which are not very well known. And that's why we keep calibrating them until we are able to match observed data. And I will talk a little bit more about that in the next couple slides. And that's basically what I just explained here. So here I discuss some of the issues when doing reservoir modeling. One of the issues is, are you able to represent the right physical mechanisms going on in the subsurface? Because what's going on in the subsurface is what you're trying to model, right? So if you're using a black oil simulator, you're using CMG IMEX, but there is a lot of chemical reaction going on in the reservoir that affects the flow rate. Well, your numerical model will not be able to predict the flow rates accurately because that IMEX simulator doesn't represent the chemical processes which may be dominant in a certain reservoir under certain enhanced recovery mechanisms. What feedbacks and or delays are needed to use the simulator? Sometimes you will need to acquire some more data, right, before the numerical simulator will be appropriate. Is the level of detail, the resolution of your model appropriate for the problem you're trying to simulate? If you're trying to figure out the best location for an infill well in this reservoir, and your grid blocks are this big, and you already have a well here, another well here, there is no way to figure out that some of these parts will be undrained, because again, each cell is like a tank, right? So this model is just not refined enough to capture the level of details needed to be able to find the regions that haven't been drained. So if you were to use a higher resolution model, then you could observe that some of these parts, some of the regions in this big cell, originally it was this big. Change the color. Originally it was this big, right? Then you realize some part of that cell hasn't been swept. So the resolution of your model is very important, depending on the physical mechanism or the process of recovery you're trying to model. Then you have enough data to support the inputs that went into all of these grid blocks in this domain. If you're just using some random values, then of course, whatever you predict is a function of the uncertainty in those parameters for all of the cells in the domain. Move on to the next slide. You went past.